Okay, I think we can start. Okay, now let me continue with the methods of coping for the bullwhip. Now, we can reduce the lead time. Of course, now I'm going to relate to the things that we have done previously. For example, you can reduce the order lead times. How are you going to reduce that? By using this cross-docking mechanism. Okay, instead of direct shipment, okay, if you use cross-docking, it means that you're going to have more information. So you can reduce the lead time by using cross-docking. Now, information lead times can be reduced by using electronic data interchange systems. This is especially important if you are giving orders. Okay, instead of calling or maybe giving specifications using fax and so on and so forth, you can simply use electronic data interchange, which is going to contain your specifications of the product that you want. So automatically from that point on, the supplier who is going to manufacture that product knows the specifications of the product design and maybe directly use it in their computer-aided manufacturing system so that everything is going to be very, very fast. Okay? So these are certain possibilities to reduce the lead time. Okay. Now, another possibility is strategic partnerships, which we were discussing during the break. Vendor manager inventory is the typical thing to do. I was giving the example of Coca-Cola in large markets. Coca-Cola actually manages their own shelves in large supermarkets, which means that the supermarket is not included in the decision-making process on how much Coca-Cola is going to be placed in the shelf. The only decision which is given with the agreement is that there is a certain shelf size that Coca-Cola is going to use. The shelf size is limited. There are some exceptions to that. When they are promoting a new material, they might use middle of corridors and so on and so forth, but shelf size is limited. And Coca-Cola personnel actually administers the control of that shelf size. It has nothing to do with the supermarket. So supermarket only gives the shelves and makes the profit, which is nice actually. And Coca-Cola is very happy with this. Why? Because basically they can now follow the real demand, and so that the chances of back orders, which is going to hurt them because they are in a very competitive market, is going to be less. So they actually manage the inventory. This is called vendor managed inventory. Most of the automobile firms actually has an agreement with their dealers using some kind of a vendor managed inventory. Now, the problem here is, of course, this is very nice. You can see that it is going to reduce the bullwhip effect. We have not talked about costs, because reducing bullwhip effect is going to cost you something. Why? For example, for Coca-Cola, Coca-Cola is now paying for the shelf. There is a fixed amount of money that they pay. At the top of that, a number of Coca-Cola employees are working in that supermarket. Okay? So this is all money, and how are they going to make sure that they are making a profit eventually is not a very simple issue. Now, moreover, how to operate vendor managed inventory is not a very simple issue. Well, it is simpler compared to most of the other parts, but it's not that straightforward. So there are still a lot of academic research going on in the area where what happens if you have the information? How are you going to operate the system? What happens if you are operating a vendor system? How is it going to be beneficial to you? Those are still some research questions which is going on in academia. In practice, they believe and solve it in a certain way, but sometimes it turns out that it might be more costly. Okay, so this is always something that you have to keep in mind. Okay. So, any questions on this? Vendor managed inventory. Now, other things which is going to prevent information sharing and incentives. So you create some incentives so that information holders are going to give the information to you. So this is basically something that you do. You have contractual incentives to get true forecasts from buyers. You can create an effective forecasting system, which is, I think, tried. There is a computer system which is called collaborative. Well, I don't remember the acronyms. Collaborative forecasting, and there are two other letters. But this is something that enables different parties to use a computer program, and in which they are going to place their own forecasting intuition, and eventually a forecast will come out of the machinery, which is something like very similar to an expert system. And then after some interactions, a forecast is going to come where all the sides are going to agree, so that all the sides of the supply chain are going to use the same forecast. So there are mechanisms which are created. Of course, you can see that this is a matter of trust, because these mechanisms are third-party mechanisms. Okay? An outsider is coming and putting up that mechanism. And in the case of forecasting, it is a non-profit organization, actually, which is doing this. So there are very nice things that people are trying. Now, of course, having all of these possibilities takes us to global optimization issues. Global optimization in the sense that, remember the Clark and Scarf paper. Okay? We said that everything is known. We have different sides. Well, actually, it is not. But what happens is that if you have information sharing, if you have some incentives to share information, if you have effective forecasts, what is it bringing is simply a centralized system where you can apply Clark and Scarf solution, for example, and so that is the solution which is going to be effective for everybody. But still, okay, we know how to do that. That's the easier part. We don't know actually what to do when that information is not complete. Okay? In other words, how do you solve Clark and Scarf when the demand information is not known, is not similar in both sides? We don't know that. Well, we have an idea, but these are difficult academic issues to handle. We know how to handle the extremes. Centralized, we know. Difficult, but we know. Decentralized, we know, because that's the classical theory. But we don't know what happens when you have some information sharing, some agreements, and some what we call, in certain cases, we have not equal information in both sides. So we call it asymmetric information. In that case, we don't know actually how to approach the problems most of the time. We have some understanding, but those are the academic issues. Now, of course, even if you solve the global problem, like Clark and Scarf, you still have the following issues. Who is going to optimize? Now, in Clark and Scarf, we optimized for the system, but in certain cases, who is going to do the actual optimization is not that clear, because if the manufacturer is doing that, then the objective function might be slightly different, so that he or she is going to have more possibilities. So this is a key issue. And let's say that we obtain some kind of savings by coordinating our operations. How are we going to share that? Okay, it's not always obvious that sharing is going to be straightforward. There is a vast literature on game theory which is trying to do these two issues. And we are going to see a few of those examples. But, I mean, the literature is pretty large. Now, what are the methods that actually address these type of issues? Supply contracts, we're going to see examples. And strategic partnerships in general is actually a remedy to the bullwhip effect that we're talking about. Okay, so this ends the slides. Any questions? Now, what I'm going to do then is I'm going to take the Lee et al.'s management science paper, and from that paper I'm going to give two examples. There are 4 models which are given in that paper. And each of the models show quantitatively the effect of the bullwhip effect that we have seen here. So in each of the models, the variance of the orders given divided by the variance of demand is calculated, and it's shown to be larger than 1, which is the quantification of the bullwhip effect. So we're going to do it in 2 different environments, and I will start with the first one. Now I will start writing it on the board. Okay. Now the first one is about demand signaling. So it is not forecasting. We are assuming that the demand is non-stationary in general. We are going to assume that demand is non-stationary, but we are not going to have any problems with respect to forecasting. We are going to assume that we know how demand is behaving. So there is no forecasting issue. So we are not going to lose any, we are not going to have any increase in the variability with respect to forecasting. But demand is non-stationary. So what we are going to do is the following. So this is Lee et al. Paper in Management Science. And this is 1997. Now, it turns out that this is one of the most cited papers, I think, in our area. In this area, well, including, I think, in operations research maybe. Although it was published in 1997, it has an enormous number of citations because it turns out that the simplistic way of showing certain very difficult notions was the main catch. And this is something that really affects the supply chains in real life. And everybody was aware of this. So in that respect, it was a very nice paper to show certain effects. Although you are going to see that there is no analytical sophistication. It's only like a few models that you write here and there. This is the beauty of the paper, actually. When you are a first comer in a certain topic, okay, the ideas are much more important. So if you are doing a research on a topic which has been used several times, then you have to be innovative with respect to the techniques that you use, the models that you propose, the approach that you take as well. Whereas if you are the first in that field, okay, you can be very simplistic. Okay, so this is a paper which is very simplistic compared to the others, of course. I'm not saying that it's a simple paper, but the models are sort of very intuitive and so on and so forth. So we're going to see 2 of those models. Okay, now the issue is demand signaling. So we don't have any forecasting problem. We are going to assume that we have a non-stationary demand process, and the model that is used to describe the demand is simply as follows. dt, demand at time t, is a constant d plus a rho times the demand at time t minus 1 plus and an error term, where rho is in between -1 and 1, and u sub t is a normally distributed random variable with a mean 0 and variance sigma square. Now, of course, and we are going to assume that ut minus 1, ut minus 2 are all independent, identically distributed random variables. So what's happening is that there is a certain mean demand, but that mean demand is disturbed depending on the value of rho on the, in terms of the previous sale. So demand in time t is going to be related to the demand in time t minus 1. Now, of course, we need to have the variance to be much, much smaller than this constant d. so that we don't have any negative demand. Okay? No negative demand. Probabilistically, of course. Okay? So this is the demand model. Now, by the way, this model is actually a model which reflects most of the regular demand patterns in the retail sector. Okay, there are certain products where if the demand was high, you expect it to increase more. But there are certain products where if the demand is high in one day, you would expect that it is going to decrease over time. Okay? For example, toilet paper is a good example. I mean, you never use more toilet paper. So if you had more demand in a given day, you expect that demand to decrease. Okay, so it is negatively correlated. Whereas if we're talking about Coca-Cola, which makes addiction, well, for the records, okay? So in that respect, you would expect that this row is going to be positive. The market share is always going to increase. Okay. Now, in this type of a model, of course, what we are going to do is, we are going to, of course, I didn't write, but we have a two-stage supply chain. We had that in the previous slides, because those are the supply chains that we are going to make quantification. So we have a two-stage supply chain, customer, a retailer, and the manufacturer. And of course, we are going to use periodic review, so an order up to policy, which is period dependent, is going to be what we are going to use. Now, it is going to be period dependent. Why? Because basically we have non-stationary demand. So the order up to point that I'm going to have now is not going to be the same that I will have next period. Okay, any questions? Okay, now let's work on the model. Now, let us assume that ST is this order up to level. Now, I'm going to assume that you use the notation in the text. This nu is the lead time. And of course, when we talk about an order up to policy, we're talking about inventory position. You already are guessing it now. So this is going to be the lead time. And let ST be the order up to level inventory position in period T. So this is the decision variable that I'm going to have. Now, what I will do is actually, I will first write the model. What I am after is, according to this model, I'm going to find optimal ST values. Okay? And given the optimal ST values, then I will be able to write the order quantities that I give every period. So what I will do is I will compare the variance of those order quantities with the variance of the demand that I have here. Okay? So this is going to give me an understanding of the so-called bullwhip effect. Any problems in the way that we are going to approach? Okay. So what do we solve actually? We solve the following problem. If you recall the multi-period problems that we have studied, so this is something that we can write. So summation from t is equal to 1 to infinity of beta to the power minus 1, where beta is the discount factor. And then I have the expectation of the following term. C times ZT plus beta to the power nu G of st, and then I have I from t to t plus nu times di. Okay, so every period actually what I do is I actually take this sum. I'm trying to minimize my discounted costs. So my decision variables are STs that I give every period, order up to point. Accordingly, ZT is going to be the order quantity. So according to this ST, I'm going to order a ZT quantity. C is going to be the unit cost. And then I'm going to have the inventory holding and backorder costs, which are going to incur lead time periods later on. Lead time plus 1, actually. If you recall, that's the way that we were able to write the problem, because the other terms are not going to be affected. And we are going to do that for all the possible values of t. So this g function is actually the backorder and holding costs. And so let me write where g of st summation I from t to t plus nu di is simply h times st minus summation I from t to t plus nu of di plus I'm going to have a pi, which is the backorder cost of, this time I'm going to have summation I from t plus nu di minus st. So this is the one period holding and backorder costs. Okay? Note that I have nu plus 1 terms here, which reflects the lead time plus the review period demand. Okay? So what we are doing is actually, if there was no lead time, in other words, if we immediately, so the uncertainty, we are bringing the system up to a level, then demand occurs. At the end of the period, we make a holding cost charge if the remaining quantity is positive. Otherwise, if it is negative, it is a backorder cost. So I am taking all these costs, but this cost occurs lead time periods ahead. Okay? And when I make the decision today. And so what I do is I minimize this function over all ST values. And the minimization of this function is going to give me when I find STs that will minimize this, I will be able to get the optimal solution. Now, note that this E1 is the expectation of demand, which is expectation of demand over lead time, plus 1 periods. Okay, so this is the expectation over lead time plus 1 periods. Now, this is, if you recall, this is what we have written when we started to analyze Clark and Scarf. But we have now written it in a little bit different way. What did we do? We took out the parts which are constants. Okay? Note that if the lead time is nu, you cannot affect anything from t is equal to 1 to t is equal to nu. Because whatever you order at time 1 is going to arrive at nu plus 1. So you can only affect the inventory at that point in time. Okay? So that's the reason why we only include that factor which I can affect with my decision. And this continues until t goes to infinity, of course, for all t. Any questions on this? This is sort of the same thing written in a little bit different way. Okay. Now, of course, in the paper, they don't solve actually this problem. But I am going to be a little bit more detailed in solving this problem. The original reference that they give is Heyman and Sobel, 1984. It's a book, Stochastic Models book. And so I am also using the notation that is given in the paper, so it means that I'm following Heyman and Sobel. So now I can write the following. Now let Z sub t minus nu plus 1, Z sub t minus nu, t minus nu plus 2, all the way to Z t minus 1 be the amounts on order. So then ST is going to be what? ST is the order up to level. And let's say that it is going to be equal to IP, the inventory position at time t. This is the inventory position before an order, inventory position before an order is given. And then plus ZT is going to yield me the order. So this is the relation. Of course, I don't know ZT, I don't know ST, I only observe IPT. But what I'm going to do is I'm going to write this STs in such a way that I am going to have two consecutive demands coming in, and then I'm going to use the process. So if I write IPT plus 1, inventory position at t plus 1, so this is before the order is given, so it should be ST, the order up to level that I have in period t, minus the demand in period t. Okay, I'm simply using the definitions. So the inventory position at time t plus 1 before I give the order is going to be ST, the optimal order up to level that I used in period t, minus the demand which incurred during that period. Okay. So from here now, if I substitute ST value here, so this is going to be IPT plus ZT minus ST. Okay, so for example, if nu was equal to 0, then the G function, okay, the G function which is defined here, I could write the G function as h of ST minus dt plus pi times dt minus st plus. If nu is positive, lead time, then I can write this as h st. Now you can see where this is leading to. You are going to have different ZTs coming into picture. Yes? Excuse me, again? Which term are you talking about? Okay, instead of, this is IPT plus 1. Okay, so I have ST minus DT. Is that the question that you're asking? Okay, next one. Oh, okay, this is DT. Thank you. Oh, okay, this is DT. Yeah, I'm sorry. Okay. Okay, now what I'm writing is I'm writing this G function in terms of the of DTs, but the way that I'm going to write is such that I'm going to show that I can write, instead of different T's, I can represent them as the ZTs, because I know that ZTs are going to be equal to the demand, well, they are related to the demand which incurred. So if I rewrite this, this is going to be summation I from 0 to nu minus 1 of ZT minus I, outstanding, minus DT plus. So how did I do this? What I need to do is basically ST minus summation of demands, but I know that the demands that I'm going to observe are going to be replaced by the quantities which are on order. So using this relation, I can write this to represent G, and then I have the other term with pi. I'm not going to write that. Okay, so what is the use of this? Well, the use of this is simply the following. From here, I will be able to write G as a function of z's. Okay, and you will see how I'm going to use that. So how did I do this? Well, you see that if I am interested in IPT minus summation I from 0 to nu minus 1 z sub t minus I minus is actually can be written as IP t minus nu plus z t minus nu minus demand I from t minus nu to t minus 1 di. Now, all these relations are possible because what I am doing is I am simply counting for the demand which has incurred before in the quantity that I am ordering. If it was stationary, I know that they will be equal, but now the difference in ST values, order up to values, is actually accounting for the demand and the order quantity. So you can see that the inventory position before I give an order at time t minus the quantities that I have ordered before but not arrived yet, okay, so this is going to give me the net inventory, is actually the net inventory at time t minus nu plus the quantity that I order, the inventory position at t minus nu, the quantity that I ordered at t minus nu minus the demand that incurred before. Because this inventory position here is all taking into account the demand that incurred. So this identity is what I have used actually to replace the G function from that form to this form. Now we're going to see how I'm going to use that. So given this relation, I have a few steps to go, which is missing actually in the Lee's paper. That's the reason why I'm doing it. And so what I have is simply the following. So I will now write ST minus summation I from 0 to nu minus 1 ZT minus I minus DT is actually equal to IP, inventory position at time t, plus ZT minus summation I from 0 to nu minus 1 ZT minus I minus DT. And from here, actually, if I go a couple of more steps, I'm going to obtain ST minus nu minus summation I from t minus nu to t of di. So this actually shows that I can write the G function that I have there. So this simply says the following. You can write the net inventory in terms of the inventory position minus the most recent stock, but at the same time you can write it as in terms of the order up to level that you had lead time periods ago minus the demands. Okay? Because basically the quantity that you ordered at that point in time is what you had. So this is going to be the quantity which you already have now physically, which you are incurring costs. So this means that this is everything is the cost that we are charging, I can rewrite this in terms of S sub t minus nu summation I from 1 to n, I from t minus nu to t di. So we see that this is the G which is going to be paid lead time periods later. This is simply a manipulation of the terms. And so if you look at this term, instead of this, I can rewrite this in that way as well. So by manipulating it, we can do the optimization in a much simpler way. Okay, so this is more or less the idea. Now let me go one step further. What you need is actually you need to go over these equations in order to understand what's going on. What I'm simply doing is manipulating the terms so that I will be able to replace ZT and replace the S values that you see in the equations so that I will be able to do the optimization in a simple way. Okay. So once I have these relations written, next step is to go to the optimization, to go back to the optimization and do the following. So what I'm going to do is I'm going to write the optimization from 2 to infinity, and I am going to take out the parts that are related to S1 only, because I'm interested in the first order that I'm going to give. Okay, and that's the way that I'm going to write the variances. Okay, the variance of the order given divided by the variance of the demand currently. I'm not going to do it for every period. I'm just going to do it for the first period. So if I have this, this is going to be C times. Now instead of ZT, I'm going to have ST minus 1 minus DT minus 1. Note that this is going to be your current Z. Why? This is the inventory position right after the demand, before you give an order at time t. And the order that you are going to give at time t is going to be ST minus your inventory position. Okay? So this is what I have. Now, I am going to assume that this is always going to be positive, and we're going to discuss that later on once we finish. Okay. And then I'm going to have beta nu times G ST, and then I have summation I from t to t plus nu of di. So this is going to be the cost of holding and backorder. Then I'm going to write these things for the first one. So I'm going to have C S1 minus IP1, inventory position 1. And then I'm going to have beta to the V, G of S1. And then I have summation I from 1 to T minus T plus nu, I from T to T plus nu di. This should be yes. And then I have some costs that are not going, some costs which are constant. C summation T from 1 to infinity, BT times DT is a constant, minus C IP1, and this is actually a constant cost. Okay. So what you can see it actually is, by writing it in this form, I was able to single out the effect of S1. So next step is basically, how am I going to approach this problem is simply as follows. Let me write this. This is equal to t from 1 to infinity of beta t minus 1 times c 1 minus beta st plus bv g st summation I from t plus I from t to t plus nu of di. So this is the form that I have eventually. And this is very similar to the original form that I have, with the only exception being that I don't have zt's anymore. Everything is in terms of st's. Okay? And how did I manage this? I basically manage this by the relations that you have seen here. So this is basically what I am going to optimize. Now you can say that this is a certain function of you can say that this is the expected value of g of st. Okay? And so g of st is going to be c times 1 minus beta st plus all this term. And what is the solution to this? You have actually news vendor problems. Note that this is like the news vendor cost. You have a certain distribution. Forget about this beta to the nu. But you have a certain distribution here that you charge, whether it is lead time ahead or now, doesn't matter. It's like newsboy style. And this is also newsboy style, with this being the unit cost. Okay? So what you have every period is, every period you have newsboy style costs. Now, given that the quantity that you order is always positive, okay, this is going to be true. So every period you are going to order up to a certain level, so it is going to be like a news vendor problem repeating itself, even if you have a non-stationary demand. So the first period, the quantity that you order in the first period, then is going to satisfy the following condition. So the quantity that you are going to order in the first period, S1 star, is going to be simply GW plus 1 minus 1. So this is the inverse of the density function evaluated at the fractile point where we have C1 minus beta divided by beta to the V divided by H plus pi. Okay, this is the equation which is given in the Lee's paper, Lee et al. 1997. This is equation 3, actually. So they simply give this after they pose the problem, and so these are the steps that are needed to obtain this. Now, what we have here is we have a news vendor problem, and we know that the news vendor problem is going to have CUs, COs, if you recall. So this is simply CU plus CO, and this term is going to be CU adjusted. Note that it is adjusted for the infinite horizon that you have in front of you. So if you cannot obtain, well, you may need to work a little bit on this G function to obtain this term. So this is the solution. Now what is important here is that this Q function is actually demand distribution inverse of the demand distribution over nu plus 1 periods. Okay? So this is basically the only thing which is a little bit different. Okay. Now, what are we going to do then? Well, now it is time to compute the variances. Okay? Now, note that S1 star is the order up to point that you are going to have. Now, what is the quantity that you are going to order is Z1. Now, what we are going to find out is simply, we want to find out the variance of Z1, which is a random term. Why is it random? Because it depends on the demands. Okay? And we are going to divide that to the variance of D1. So this is going to give us the bullwhip effect. And so question is, how are we going to find Z1? And how are we going to find the variance of D1? Now, next thing is we are going to use the demand process itself. Now, the rest of the material is actually given in the text, but I'm going to go over them as well. So how are we going to start with this is simply as follows. Okay, so let me initiate the analysis. So we're going to have dk, which is d plus rho times dk minus 1. Okay, this is the demand relation, plus uk. And now you see that I can rewrite dk minus 1 using the same relation. So this is going to be d plus dk minus 2 times rho plus uk minus 1 plus uk. And if you continue on doing that, dk can be written as d. You have an infinite series coming in. Okay, 1 minus rho k divided by 1 minus rho plus rho k times d0. Well, it's not an infinite series, excuse me, it's a finite series because I'm talking about k, and it is going to go all the way to d0. Okay, so this is d0. Plus I'm going to have summation I from 1 to k of rho to the k minus I times ui. Okay, so what I have done is I have represented dk in terms of d0. Now, why did I do this? Because I will be finding demand over lead time. So now for all the D1, D2, D3, D4, D5, D new, I'm going to add all of them up, okay? And I will try to find demand over lead time. So next time, on Thursday, I'm going to start from here, and I will simply try to find out the variance of demand first, and then I will find the variance of the quantities that I order given this S1 optimal. Okay? We'll see how I will be able to write that. And after that, I'll start to the other model, and the other model is shorter, and I'm hoping to finish it next time. Now, the key here is actually, if you look at these terms, I think I would recommend you to look at these equations and see how they actually evolved. It's not difficult, you only need to follow the definitions. Okay, I know that I have been a little bit quick in passing all these equations. Okay, any questions? They are all at the reserve since the beginning of the semester. Everything is placed at the reserve. All the material is placed at the reserve.